Hi, welcome to Transformer Rubberband Theory. My name is Scott Meineke. I'm a job training and safety instructor for the Iowa Association of Electric Cooperatives. I put this program together to try and help our line workers understand basic three-phase, delta, Y connections, and troubleshooting. Let's think of a transformer. A transformer itself has to have energy applied to it, so energy will come out of it. They're an amazing device. There's no moving parts inside of that transformer. They just work on electromagnetic induction. A transformer sitting on the ground has no energy. It has to have a difference of potential applied to it. To make that comparison to a rubber band itself has no energy. It has to be stretched between two differences of potential in order to have energy applied to it. Commonly, a transformer is connected from a neutral wire to a phase wire. That's where it gets two differences of potential in order to get power. We're going to use a red push pin to represent A phase and a green push pin to represent the neutral. We'll take the rubber band and we'll stretch it from the red push pin, A phase, to the neutral. It now has energy applied to it, just as the transformer has energy applied to it. Sometimes transformers are connected between two phase wires. We'll use a red push pin to represent A phase and a yellow push pin to represent B phase. And again, we'll stretch from A phase to B phase. Now energy is applied to that rubber band. Let's take a look at 3 rubber bands and several push pins. We'll put the first red push pin in the lower left-hand side to represent A phase, the yellow push pin in the center top to represent B phase, and the blue push pin in the lower right to represent C phase. A phase, B phase, C phase. We're not using the neutral right now since it's a true delta system. We'll then stretch a first rubber band from A phase to B phase. We'll stretch another rubber band from C phase to A phase, and yet a third from C phase to B phase. We've created a delta system by doing this. Of course, the transformers or rubber bands have to be rated to stretch between the phases instead of phase to neutral voltage, but this is a delta connection. Very simple to make. Let's take a look at the Y system. Same 3 rubber bands, same push pins. We'll put the red push pin in the lower left, yellow push pin center top, blue push pin lower right. This time, we'll go ahead and put the green push pin in the center. These represent A phase, B phase, C phase, and the neutral in the Y configuration. We'll take a rubber band, stretch it from A phase to the neutral, another from B phase to the neutral, and another from C phase to the neutral. We've just made a Y-connected bank. Now, there are some variations of a Y-connected bank. First, we say this is a bonded or grounded Y point. We say that because the green pin sticking in the center through the Y point connection is bonded representing the neutral wire. They are physically and electrically connected to ground. Sometimes, in some applications, we float this Y point or unground it, with the Y point all tied in a knot in the center here. So all of these rubber bands are tied in a knot. If I were to pull that green stick pin out that I just did, that neutral would come out almost in the same position. It really wouldn't move much. Now, based on load, it will move around here. So it needs to be fully insulated. In fact, if I were to lose a phase or another phase, you can see very quickly with rubber bands, we would want to make sure that we had that insulated. Let's go back to the delta. Take a look at it. With the delta rubber bands, what would happen if I came down here and I pulled out this pin? Well, it's very easy to see those rubber bands would snap over. 2 would be in series phase to phase. 1 would still have same voltage applied. What's going to happen? What's going on with the voltages now? Well, using trigonometry, we would find out that we would have half the voltage times 1.732 would be the voltage from the far phase to the neutral. One side still has normal voltage on it. The other two, about half the normal voltage on them. Now, I say about half because since there's no connection to that center of those two, where the C phase used to be, based on load, it'll fluctuate around, so it won't be equal on both sides. Notice we also lost any vector that was there. So we lost any capability of having three-phase when we lose one phase of a delta system. Let's take a look at the Y system now. We'll go to C phase again and lose it. C phase comes out. What's going to happen to the rubber bands? They snap over. We've lost one phase. If we look at the vectors on the side, we still have two phases. Notice this phase and this phase are still there and energized. We have lost the third phase, however. If this was a Y secondary with a Y primary, we lost the three phase, and this customer is going to call you. Let's do it again. Lose that phase. Obviously, the rubber bands, they're going to snap over. We lost one phase there. Still have two phases energized as we did before, but what if it's a delta? In this case, with a delta secondary, two of the transformers still have full voltage on them, right? They also still have an angle between them. So as we look at the secondary vector here, we still have a normal triangle, just missing one side. In fact, this is what we call an open bank. This is how we build an open bank. We just don't use this third transformer. You have to remember to ground the Y point though, otherwise it doesn't work. But since there is a transformer core still there, and the secondaries are still energized, it will then backfeed that transformer and re-energize that third phase and provide it back for you. Now, if that's on the bank itself, it's not that big of a deal. But what if this open, rather than here, was somewhere way down the line and we had a lot of other customers that were being fed by it? That would cause a lot of problems. So when a phase or a transformer is lost, this one becomes an open bank automatically. Now, it's not going to have the same capacity as a closed bank would. It's going to have a much reduced capacity. In fact, it's 57.7% of the original capacity of the bank. So it probably will overload the other transformers when it happens. But the worst part is it has the potential to backfeed the entire line at full voltage. So what if we float it, right? We're going to have the floated Y point this time. So we've removed that neutral. The Y point's floated in the middle. What if I pull C phase again, right? If I pull it out, these snap over, right? They're going to snap over, and that's what we're going to end up with, very obviously, right? Well, let's start putting things back into position. First we lost our phase angle, so we lost our three phase. The neutral is still there, even though we didn't bond to it. The neutral is still in that position. Well, neutral to C phase is your phase to neutral voltage, as it was before. What about the distance from the Y point now? Well, if we vector this out, right, we end up discovering that this is half of the primary voltage still, from where the neutral is to where the Y point is, half the primary voltage. Well, when I go to close this gap, let's look at this. Since it's half that voltage, if I go to close this gap from the C phase here all the way to that Y point, it's 1.5 times the voltage that was supposed to be there. This is why a lot of times you find failed lightning arresters near this bank. It's that high voltage surge. Well, I hope this helps quite a bit when you start looking at rubber bands and how these things work and explaining some of the voltages. The delta, of course, is pictured on the left. The Y is pictured on the right. If you think about your transformers as rubber bands, it'll assist you with troubleshooting in the future. Good luck. Thanks for watching. You can see more of our transformer connections on our Iowa Association of Electric Cooperatives YouTube channel. I would encourage you to go there and look at what we have. Thank you very much, and be safe.